December 20th, 1967. Penn Station. Morning rush hour. A silver train, unlike anything in the station, slid away from the platform, past commuters still boarding conventional coaches on adjacent tracks. Through the Hudson Valley, it accelerated past automobiles, past freight trains, past the speed limits that had governed American railroads since the 1920s. 170 miles per hour on tracks laid for steam engines. The few passengers aboard likely felt something had changed permanently. This wasn't just faster, it was different. By winter 1976, that feeling was gone. The last TurboTrain had made its final run. No ceremony, no announcement. It simply stopped appearing on the timetables. In 1967, building the fastest passenger train in American history felt like inevitability rather than ambition. High-speed rail wasn't a dream imported from abroad. It was the next logical step for a transportation system that had always adapted when older technologies reached their limits. European systems were setting speed records with serious government backing. The Japanese had proven that steel wheels could outrun airplanes on certain routes. American engineers weren't content to watch from behind. The federal government was funding infrastructure projects that seemed impossible a decade earlier. Interstate highways crossed mountains and deserts. NASA was putting humans into orbit and bringing them back alive. Building fast trains seemed straightforward by comparison. The promise was specific. Trains fast enough to compete with airlines on corridor routes between major cities. Not faster than what existed, but fast enough to matter. The TurboTrain would prove that American passenger rail could reclaim relevance through performance rather than nostalgia. At United Aircraft Corporation, engineers approached the problem like they'd approach any aircraft challenge. Traditional trains had one locomotive pulling passenger cars. The TurboTrain would distribute gas turbine engines throughout the train. Each car powered itself. The train would accelerate like no conventional locomotive could, because power came from everywhere instead of one point. The design looked like speed, aerodynamic nose, smooth surfaces, large windows that made conventional trains seem quaint. Inside, aircraft-style seating and individual climate control suggested transportation for a different era. The ride felt different too. Aircraft suspension systems absorbed track irregularities that made conventional trains rock and sway. Gas turbine engines from aircraft applications had proven reliable for thousands of hours in demanding conditions. This wasn't experimental technology. This was integration. Testing went exactly as projected. The trains reached design speeds safely and consistently. They rode smoothly. They accelerated quickly. Federal officials witnessed demonstration runs that validated every engineering assumption. Existing tracks could handle the trains without major modifications. Everything matched the projections. Then came Tuesday mornings. The TurboTrain entered passenger service between New York and Boston in April 1969. It also operated from New York to Montreal and between Chicago and St. Louis. Real passengers, real schedules, real weather. Passengers appreciated the speed and comfort when everything worked properly. Everything didn't work properly. Gas turbine engines that ran efficiently at 35,000 feet consumed fuel voraciously at ground level. Operating costs exceeded projections immediately, not by small margins. The engines required maintenance procedures that most railway shops had never encountered. Aircraft components operated on replacement schedules designed for aircraft, not trains making daily round trips on routes that hadn't changed since the 1940s. Curves that conventional trains navigated comfortably at 79 miles per hour became problems at 125 miles per hour. Banking designed for freight trains carrying grain created uncomfortable lateral forces when passenger trains tried to maintain aircraft speeds. Track maintenance standards that had served adequately for decades proved insufficient for consistent high-speed operation. Signal systems created bottlenecks that negated speed advantages. Stations weren't equipped for the TurboTrain's specific boarding requirements. Platform heights were wrong. Baggage systems needed modification. Weather affected the system in ways nobody had anticipated during controlled testing. Snow accumulated on aerodynamic surfaces and changed performance characteristics. Summer heat stressed air conditioning beyond design limits. Winter cold influenced engine efficiency more dramatically than diesel locomotives experienced. Most significantly, the TurboTrain needed maintenance that the existing railway system wasn't prepared to provide. A maintenance supervisor in Boston later recalled those early months. We knew it was Tuesday because the TurboTrain was broken again. Mechanics required specialized training that went beyond traditional railway skills. Parts took longer to arrive than conventional railway equipment because aircraft supply chains weren't designed for daily railway operations. The maintenance schedule demanded more attention than traditional trains. More downtime, more complexity, more cost. When one engine failed, the train could continue operating on remaining power units, unlike locomotive-hauled trains that lost all power immediately. But when multiple systems needed attention simultaneously, the train went out of service for days rather than hours. Winter mornings were particularly challenging. The heating systems, designed for aircraft cabin environments, struggled to maintain passenger comfort in stationary trains during extended station stops. Ice formed in places that conventional train heating had never needed to address. Equipment designed for constant aircraft motion didn't perform optimally when trains sat motionless in stations for passenger boarding. Mechanics would arrive at maintenance facilities on cold mornings to find systems that had functioned perfectly the previous evening, now showing fault indicators. Components that worked reliably at aircraft altitudes proved sensitive to temperature variations that conventional railway equipment handled without difficulty. Summer presented different but equally persistent problems. The air conditioning, adequate for aircraft at altitude where outside temperatures were predictably cold, worked harder at ground level and sometimes failed entirely during peak heat periods. One July afternoon in 1971, a TurboTrain bound for Boston sat motionless at Penn Station for 45 minutes while mechanics diagnosed an air conditioning failure. Passengers watched through the large windows as conventional trains with working climate control departed on schedule. By the time repairs were completed, most passengers had transferred to other trains. The few who remained arrived in Boston 2 hours late on a day when the TurboTrain was supposed to prove its superiority over conventional service. Passengers boarding in New York expected aircraft-level comfort throughout the journey. When systems couldn't deliver that comfort consistently, passenger complaints accumulated quickly and undermined the premium service reputation that justified higher fares. Ridership grew, but not fast enough to offset the elevated operating costs. Business travelers valued the time savings when service operated on schedule. Passengers enjoyed the superior comfort when mechanical systems functioned properly. The TurboTrain attracted riders who specifically chose rail service because of the speed and amenities. But mechanical issues caused delays and cancellations more frequently than conventional trains. When one TurboTrain required unscheduled maintenance, replacement equipment wasn't always available. Passengers who specifically chose TurboTrain service for speed and reliability found themselves on conventional trains that couldn't maintain advertised schedules. The pattern established itself quickly and predictably. Monday mornings often brought reports of weekend mechanical issues that required attention before passenger service could begin. Problems that developed during Friday evening service consumed weekend hours when conventional trains sat idle and required minimal attention. Maintenance staff found themselves working schedules that conventional railway operations had never demanded. Gas turbine engines needed attention at intervals that didn't align with traditional railway maintenance cycles. Systems that required daily inspection in aircraft applications needed the same attention in railway service, but railway operations had been designed around weekly or monthly maintenance schedules. Friday evenings saw trains limping back to maintenance facilities for repairs that would consume weekend hours. What started as minor adjustments often revealed additional problems that required parts ordering and extended downtime. The sophisticated systems that provided superior passenger experience created maintenance dependencies that conventional trains simply didn't have. Mechanical problems became more frequent as equipment aged under the stress of daily high-speed operation. Equipment availability declined as maintenance requirements consumed more time and resources. The sophisticated systems that provided performance advantages created operational complexities that overwhelmed those advantages. By 1972, the arithmetic had become clear to everyone involved. The cost of maintaining sophisticated equipment exceeded revenue from passenger operations by margins that made continued operation economically impossible. Federal subsidies covered some expenses, but the fundamental economics remained unchanged. Higher performance required higher maintenance costs that passenger fares couldn't support. Railway executives conducted reviews. Federal officials examined operational data. United Aircraft analyzed performance metrics. The conclusions were consistent across all assessments. The trains performed exactly as designed when properly maintained. The cost of proper maintenance exceeded passenger revenue by unsustainable amounts. The meetings where these conclusions were discussed were not dramatic. No one accused anyone of failure or incompetence. The technology worked. The engineering was sound. The market existed. But the system couldn't sustain itself economically within the constraints of existing railway operations and passenger fare structures. There was no crisis, no dramatic failure, no scandal or safety concern that forced immediate action. The decision emerged gradually from budget meetings and operational assessments that concluded resources could be better allocated elsewhere. Higher-speed conventional trains might not achieve TurboTrain performance, but they could operate reliably at sustainable costs. Nobody wanted to abandon the system. Everyone recognized the technical achievement. The TurboTrain had proven that American engineering could create passenger trains faster than anything operating anywhere else in the world. But proving technical capability and sustaining daily operations were different challenges that required different solutions. Service ended gradually rather than dramatically. Routes were discontinued individually, as equipment became unavailable for maintenance. Service frequencies were reduced as ridership declined and costs mounted. The remaining TurboTrains operated less frequently, primarily during peak travel periods when premium pricing could partially offset elevated operating costs. The last TurboTrain made its final passenger run in 1976, 7 years after entering commercial service. The termination of service was announced in railway industry publications, but attracted little attention from mainstream media. Most passengers didn't realize they were witnessing the end of American high-speed rail's first generation. Amtrak, the National Passenger Rail Corporation created in 1971, inherited the TurboTrain fleet from the private railroads. The new agency conducted its own operational analysis and reached identical conclusions. The trains were technically sophisticated and provided superior passenger experience when maintained properly. The cost of proper maintenance made operation economically unsustainable. Some units were transferred to other routes for experimental service, but these trials reached the same conclusion. High-performance equipment required high maintenance costs that passenger revenue couldn't support. Some units were sold to Via Rail Canada, which operated them for a few additional years before also determining that maintenance costs exceeded operational benefits. Eventually, Amtrak retired the entire fleet. The decision was made gradually, as individual trains required major overhauls that cost more than replacement with conventional equipment. Some units were sold to foreign railways for experimental programs that had access to different economic structures and operational assumptions. Others were scrapped after removal of usable components. The specialized maintenance infrastructure created for TurboTrain service was converted to other purposes or abandoned. Training programs for gas turbine maintenance were discontinued. Supply contracts with aircraft parts manufacturers were terminated. The institutional knowledge required to maintain the trains dispersed as mechanics moved to other assignments. Today, one TurboTrain sits in the Danbury Railway Museum in Connecticut. Visitors can walk through the passenger compartments and examine the aerodynamic exterior, but the gas turbine engines are permanently silent. The sophisticated suspension supports only the weight of curious tourists examining seats and interior fixtures that once seemed like the future of American transportation. The train serves as a monument to technical achievement and economic reality. Every system functions exactly as designed. The engineering is sound. The concept was valid. But the train will never again accelerate to 170 miles per hour because the infrastructure required to sustain such performance no longer exists. The tracks that carried TurboTrains at record speeds now see conventional trains operating under the same speed restrictions that existed in the 1950s. Amtrak operates locomotive-hauled passenger service on routes where TurboTrains once demonstrated that faster was technically possible. The speed limits haven't changed. The tracks are the same. The ambition is gone. Acela trains, introduced by Amtrak decades later, achieve similar speeds using entirely different technology and substantially higher government investment in infrastructure upgrading. The fundamental challenges that limited the TurboTrain remain. Specialized equipment requires specialized maintenance, which costs more than conventional alternatives. Advanced systems must operate profitably within existing economic and institutional frameworks designed for different technologies and different assumptions about acceptable costs. The TurboTrain story isn't unique in transportation history. Advanced systems regularly perform exactly as designed while failing to survive in the economic environment that must sustain them. The TurboTrain succeeded at everything it was designed to accomplish. It failed at everything it needed to do to keep existing. And that leaves an uncomfortable question. Not about trains, but about how many systems today are still being built on assumptions that feel inevitable until they aren't.